Hello everyone, this is Professor Roman. Welcome to the 24th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, I want to talk about counting antichains. I'll define for you what an antichain is. This is a little bit specialized, a little bit advanced, but not to panic because it's not going. This material won't be used in the rest of the course. So I hope you will hang in there and listen to the video, watch the video, and see what you think. It is quite interesting, really, at least in my opinion. Okay, let's begin. So this is a problem that has still no solution after roughly 125 years. One of the most interesting sub-branches of combinatorics is the study of special families of subsets of a finite set. And that's what an antichain is. It's a special family of subsets. Here's the definition. A family script S of A1 through AN of subsets of a finite set X is called an antichain over X if no member of the family is contained in any other member of the family. So here it is in symbols. I different from J implies A sub I is not a subset of A sub J. This is not a complicated condition. It's not intended to be a complicated idea. We already know what a chain is. A chain is a totally ordered subset, which means given any two elements of the chain, one is contained in the other. These are a chain of subsets. But here is just, well, kind of the opposite. That's why they call it an antichain. No subset in the antichain is contained in any other subset. Antichains are also known as Sperner families, after a German mathematician named Edmund Sperner. But I like antichain, and that's the term I'm going to use for the most part. But Sperner's name will come up, and you'll see why there's a connection there. So example, if X is this set 1 through 6, then these three subsets form an antichain over X because none of these subsets is contained in either of the other two. The only chance for that would be the doubleton subset being contained in one of the tripleton subsets, but that's not the case. This is not an antichain because the doubleton 2, 3 is contained in the set 1, 2, 3. If X is a set of size n, and K lies between 0 and n, then the family of all subsets of X that have size K is an antichain. It's an antichain of size n choose K. That's how many subsets there are of size K. Because no subset of size K can be contained in a different subset of size K. The singleton subsets, for example, form an antichain or Sperner family. Well, a natural question then for those of us who are interested in such things is how many different antichains can be formed from a set X of size n. So we have the antichain of all singleton subsets, the antichain of all doubleton subsets, all the way up to the antichain of all subsets of size n. There's only one subset in that a family, so it's a kind of an antichain by default. But there are antichains where the subsets may have different sizes. So that's not a complete list. For n greater than or equal to 0, the number d sub n of antichains over a set of size n is called a Dedekind number, named after a very brilliant mathematician named Richard Dedekind, who defined this concept in 1897. And here are the first few Dedekind numbers. And as you can see, they get a tad large. D8 wasn't determined until 1991. So 100 years after Dedekind first introduced this idea. At this time, no other Dedekind numbers are known. Okay. Let's take a look at the first couple. For n equals 1, we just take a set of size 1, so it may as well be the set containing x. The subsets of this set, capital X, are the empty set and the whole set itself. So the possible families of subsets are the empty family with no subsets of capital X, the family I called F2, which just contains the empty subset, the family F3, which just contains the full set, which is a subset of itself, and the family F4, which contains the empty subset and the whole set. The first three are Sperner families, kind of by default. No member of the family is contained in any other member because there's only one member, or in this case, no members. This is not a Sperner family because the empty set is a subset of capital X. So we got 3 Sperner families, and that's why D1 is equal to 3. When n is 2, D2 is 6. Let's see if we can reason that out. We'll take the set capital X to be little x, little y. These are the subsets. Empty set, singleton subsets, the whole set. So the families of subsets, well, there's a bunch. The empty family. These are the singleton families. In other words, the families with a single subset. Empty subset, singleton X, singleton Y, the whole set, capital X. Doubleton families. 3 of them contain the empty subset together with another subset. Singleton X, singleton Y is a family of subsets. Singleton X, the whole set. Singleton Y, the whole set. We have the tripleton families. And then this shouldn't be, this should be the power set, really, I should have said. Okay. These are all the subsets. Well, I'm going to let you go through this list and pick out the Sperner families, or antichains. One thing that's very helpful in doing this is if the family contains the empty subset, unless that's all by itself, it's not a Sperner family. It's not an antichain because the empty set is a subset of every other set. So you can immediately get rid of F6, 7, 8, and 12, 13, 14, and 16. They are not antichains. Well, so it seems like we as mathematicians are not having a whole lot of luck finding the Dedekind numbers. So what do you do when that happens? You try to find a question you can answer. What is the maximum size that an antichain on a set of size n can have? How big, how many subsets can there be in an antichain? Okay. This isn't a trivial question, but we can do some work on this. First, we need a lemma. It's called the Lubel-Yamamoto-Meshkelin inequality. And so for obvious reasons, it's usually abbreviated LYM inequality. Now let me warm up a little bit on this so we don't plunge right into it. This is an earlier antichain we looked at for the set 1, 2, 3, 4, 5, 6. 3 subsets, antichain. 2 of these subsets have size 3, 1 has size 2. And we're going to be interested in the number Sk of subsets of a given size k. So in this case, S2 is 1. There's one doubleton subset in the antichain. S3 is 2. There are 2 subsets of size 3. As to subsets of size 0, 1, 4, or 6, there are none. Did I miss something? 5. Okay. Okay. So those are the S numbers, and they're relevant to the LYM inequality. So I wanted to introduce them. Now, notice something else. If I take, I can ignore the ones that are 0. If I take S2 and divide by 6, choose 2. 6 is the size of the underlying set, 1, 2, 3, 4, 5, 6. And 2 is the subscript here. S2 divided by 6, choose 2, plus S3 divided by 6, choose 3. And as I said, you could do the same for all of these, but you're going to get 0. And you add these up, you get 1/6, which is less than or equal to 1. You say, so what? Stay tuned. Okay. Remember, we've already discussed if S is a set of size n, then the family of singleton subsets of S is an antichain, and there are n members of that family. So S1, the number of members of the antichain of size 1, is n. And all the other SKs are 0. S1 divided by n, choose 1, is n divided by n, which is in fact equal to 1. The LYM inequality is a generalization of this, of these 2 examples. Let S be an antichain over a set X of size n, and let Sk be the number of subsets in the antichain of size k. Then the sum over all possible k's, 0 to n, of Sk divided by n choose k is less than or equal to 1. And whenever you have an inequality, you are supposed to ask, when could it be? Could it be an equality at some time? And if so, hopefully, when? Well, what we can say is this cannot be improved. because of so I maybe I should make this equal, I don't know. Okay, so you can't improve on this. You can't replace 1 by a smaller number. Okay, how to prove this? Consider two distinct subsets in the antichain. Call them A and B. And suppose that A has size K and B has size J, and we can assume that K is less than or equal to J, otherwise we just reverse the roles of A and B. Now, arrange each of the n elements of the whole set X by first placing the K elements of A in any order you want, followed by the remaining n minus K elements that are not in A. So this is what it looks like. Arrange the elements of A in any order you want, and then arrange the rest of the elements in any order you want. That's a permutation of the set capital X, a very specific type. The elements from capital A come first. Okay, that's the only requirement. Suppose we let P sub A be the set of all such permutations. So you can scramble the A's any way you want in the front, followed by some scrambling of the rest of the elements of X. How big is the set P sub A? How many ways can you do that? K factorial times n minus K factorial. Do the same thing with the other subset B. So you'll get permutations where you scramble B, the elements of B first, then you scramble the rest of the elements. And similarly, the size of P sub B is J factorial times n minus J factorial. Now, here is the key point to doing all this. These two sets, P sub A and P sub B, of permutations are disjoint. Because if there was a permutation, I called it pi, that's in both P sub A and P sub B, it's going to look like this because it's in P sub A, and it's going to look like this because it's in P sub B. The little a's come from capital A, the little b's come from capital B, little x's and y's come from capital X. We're assuming K is less than or equal to J, which we can do. When two permutations are equal, it means corresponding elements are equal. Therefore, the first K elements in this list are identical to these. In other words, A1 equals B1 all the way up to AK equals BK. Well, that's the same as saying this subset is contained in this subset. That's not allowed in an antichain. A cannot be contained in B. So we have a contradiction to the fact that S is an antichain. The only way out, these are disjoint. For any two subsets in the antichain, the permutations that you form from those subsets are disjoint. There's nothing in common. So the sum of the sizes of these sets P sub A, as A ranges over the entire antichain, the sum of those sizes has to be less than or equal to n factorial, which is the number of permutations of X. But now we can use this and stick it in here. Oops. Can I do this? I guess I can't. Okay. Anyway, you put it in here under the summation sign, and this is what you get. Okay. And when you divide by n factorial, you get the LYM inequality. This is probably the, let's say, most difficult proof we've had so far. Okay. If you go over it enough times, I feel confident you will understand every step. What you may not understand is who thought of this and how did they think of it. That's the cleverness that, is not something that you can teach. It's just, it comes with a little bit of talent and a lot of practice. Okay. What do we do with the LYM inequality? Well, we prove Sperner's theorem. If X is a set of size n, and if S is an antichain over X, then the size of S is less than or equal to n choose greatest integer in n over 2. That should look familiar when we talked about the sizes of binomial coefficients. This is an upper bound on those sizes. Oops. Okay. This upper bound is actually realized by taking the family of all subsets of X of size greatest integer in n over 2. As long as all the sets have the subsets in the antichain have the same size, as long as all the sets in the family have the same size, that family is an antichain. That's what we've been talking about. So how do we use the LYM inequality to prove this? Well, again, S sub k is the number of subsets of size k that belong to the antichain. This is what I just mentioned. We know that the binomial coefficients are less than or equal to this one. And so if we stick these two numbers in the denominators, same numerator, it reverses the sense of the inequality. Sk divided by n choose floor of n over 2. Floor is another way to say greatest integer n, is less than or equal to sk over n choose k. Then we just sum over k. And this is the LYM inequality. So this sum here is less than or equal to 1, but the denominators are all the same. So they can come out of the summation sign, move them to the other side, and we get the result. Do not be the slightest bit discouraged if this was too much. You have two choices. Go over it until it begins to make sense, or just move on. It won't hurt you if you just move on. But it's a challenge if you want to go over it. And I guarantee you that if you are a little confused and you go over it enough times, it may take several times, when the light goes on, it'll make you feel good. Okay. Now, there was a very brilliant mathematician by the name of Garrett Birkhoff. I actually knew him, I just met him at a Harvard gathering when I was teaching at MIT. He seemed like a very nice gentleman. He was a friend of a very close friend of mine. He conjectured that the Dedekind number d sub n is always divisible by 2n minus 1 times 2n minus 2. Well, d5 is not divisible by what it would be here. It's 9 times 8 is 72. Why do I bring this up? Well, I bring it up just to point out that even the most brilliant of mathematicians can sometimes have faulty intuition. So when I have faulty intuition, which is quite often, I don't feel quite so bad. Finally, there is, in fact, a simple formula for d sub n, found in 1988 by this gentleman, Kesselweiss or Kesselvich, Keiselvich, I'm not sure. Here's the formula. I don't think I've ever seen a mess like this before. And where this gentleman found this formula, how he found it, I have no clue. I have not tracked down the paper that he presumably published. And quite frankly, I shouldn't say this, but I don't care. It is kind of interesting that something this complicated actually gives you some simple numbers. B sub I to the k is not the kth power of b sub I. It's the ith bit, so it's either a 0 or a 1 in the binary expansion of the number k. So it's this value. I don't know what to say about this formula other than the obvious fact that it's kind of fascinating and the obvious fact that it's useless. For n equals 9, if you plug that in here, the number of terms in this summation is 2 to the 512, which is roughly 1.341 followed by 154 zeros. So you could never use this formula. But it is curious, I think. It's weird. Okay. That's it for Antichains. I hope you got something out of this video, and if you found it irritating, I apologize. But anyway, thanks for watching, and I hope to see you in the next video where we'll come back down to earth.